All right, so here's the third example of finding eigenvalues of a matrix. We're not going to find the eigenvectors here. But the wrinkle is that we're going to find the eigenvalues of this matrix A that has an arbitrary constant k in it. So the question is to find the eigenvalues of that matrix A and give conditions on k, an arbitrary constant, such that the eigenvalues are real and distinct. Okay. Well, the characteristic equation is the determinant of 1 minus lambda 2k 3 minus lambda equals 0, right? Or 1 minus lambda times 3 minus lambda minus 2k is 0, right? So if I LOIF it, last is lambda squared. Outer and inner together gives me, we did this last time, minus 4 lambda. The first term is plus 3. And then I get minus 2k is 0. All right. So hopefully remember the question. So there's no way I can factor this. I guess I could, could maybe complete the square, but let's just see quadratic formula. All right, we get lambda is minus b, which is 4, plus or minus b squared, which is 16, 4 squared, or negative 4 squared, minus 4 times a, which is 1, times c, which is c is 3 minus 2k, but I have to put those in parentheses, right? All over 2. 2a, and a is 1. Okay, so this is 4 over 2, plus or minus, all right, square root of 16 minus 12 plus 8k, right? Minus, plus, all over 2. That's 2 plus or minus 16 minus 12 is 4. That's inside the square root all over 2. So this is 2 plus or minus, all right, well, let's call this square root of 4 times square root of 1 plus 2k all over 2. Because this is 4 times quantity 1 plus 2k. All right, so that's just 2. So this, the eigenvalues, and then 2 over 2 is 1. The eigenvalues lambda are 2 plus or minus 1 plus 2k inside the square root. That's the first part. Well, let's see if it works. We had example 1. Let's see if it works for example 1 and example 2. Example 1, we had k is 0. We had lambda is 2 plus, this gives us lambda is 2 plus or minus 1 plus 0 is 2 plus or minus 1, which is 1 and 3. That's what we got. In example 2, we had k is negative 1, right? Yeah, k is negative 1, 1, 2, negative 1, 3. And this gives us lambda is 2 plus or minus square root of 1 plus 2 times negative 1. That's 2 plus or minus 1 minus 2. 2 plus or minus square root of negative 1. 2 plus or minus I. That's what we got, for example 2. So it's probably right. Okay. So we've done the first half of the question. Find the eigenvalues for any k. And then the second part is, what are the conditions on k so that the eigenvalues are real and distinct? So lambdas are both real and distinct if and only if 1 plus 2k is positive. If 1 plus 2k is negative, that's where you get the complex eigenvalues. And if 1 plus 2k is 0, the eigenvalues are 2 plus or minus 0. Right? So this is 2k greater than negative 1. I can subtract 1 from both sides of the inequality, don't mess with it. I can divide by 2. So k is greater than negative a half. That's a condition on k that gives real and distinct eigenvalues. Okay. Remember, I have to flip the inequality if I multiply or divide by a negative number, but I'm not doing that here. So all these inequalities point in the same direction. Cool. So you have a Weber problem a little bit like that. All right, well, I know there's a lot of work to do these eigenvalues and eigenvectors, but just follow step 1 and step 2 and you know, hope it works. All right, have to check your algebra lots of times probably. I know it's not going to be easy. All right, so stay well and have fun on this set. Peace.